Okay, it's the 1 o'clock rock, but you knew that already. It's Research in Manoa on Monday. And Samuel Murphy from HIGP joins us today. He's a postdoc in volcanology at the Hawaii Institute of Geophysics and Planetology. And today we're going to talk about volcanoes, I added this word, eruptions, okay, and wildfires. Yes, there is a connection, right, Sam?
Absolutely.
Thanks for coming on the show.
Thank you. I'm thrilled.
So tell us how you connect volcanoes, eruptions, and wildfires. What's the common denominator in all of that?
Right. Well, for me at least, some work that we were doing previously was on detecting hot targets from space. So it can be lava flows or wildfires because they all give off quite a lot of energy in the infrared. So we can use satellites to basically to detect them and to quantify some of their properties, like how much energy they give off. And so that's the connection, I guess, between the two, because you can have similar techniques to study the two different phenomena.
So you're looking for heat on the Earth's surface, and you see the heat from an eruption, I guess, and you see the lava, and you can see it as a graphic physically.
Yeah.
And then you can also see a wildfire because it also has a heat signature.
Exactly.
But the signatures are different, right?
Well, in a way, they both are radiating energy, just like the sun does, but they're radiating their own energy, and that you can see that using different kinds of infrared sensors. And so, in that way, they're quite similar. It's a similar problem. But yeah, in wildfires, you might have some kind of smoke covering the signal, whereas in volcanoes, it might be some kind of ash cloud or something that can complicate the issue a bit, but fundamentally, they're very similar.
If I gave you, say, an infrared picture of a volcanic eruption and lava, and I gave you another infrared picture of a wildfire, could you tell the difference right away? What's the difference?
Yeah, I think I could, mainly based on the context. So volcanic sort of signals will have to be near some volcano somewhere, almost always. Unless you get some new volcano sprouting up somewhere, but that's really rare. So typically, it'll be in the middle of lava that had flowed by previously. Whereas on the wildfire side, you might see, there'll be lots of vegetation about the place, and it gives you a clue. Also, one interesting thing is the shape of the two is probably quite different. Lava flows tend to have the sort of a flow-like shape if they're channelized.
Viscous look somehow, yeah?
Yeah,
and
right.
The wildfire has a more ragged look because it's vegetation burning.
Yeah, absolutely, yeah. And yeah.
So, okay, we got a satellite up there, and it's got sensors on it. Who owns the satellite? Who operates the satellite?
Right, so most of the satellites that I work with, well, all the satellites that I work with are NASA satellites. Most of the sensors were also developed by NASA as well. One of them there's also a Japanese space agency sensor that I work with too. But it's mainly mainly NASA.
Is NASA free about this?
Yeah.
They give you this data, they don't charge you anything for it?
Yeah, it's free. It's no cost to the end user. So they've really pioneered the way, this way of basically giving data to scientists for free so that they can come up with new science questions and answer them, basically.
So that's very nice of them. Do they
great,
ask
yeah.
anything as a quid pro quo, or do they just give it to you and let you do whatever you want with it?
I think they just want their missions to be useful, and they have this philosophy that if they just put it out there, it's going to be more useful. When you do the work, you should say, I used a NASA satellite in official publications and so on. Yeah. But I mean,
do you send them your articles? Do you say, thanks guys, and here's what I learned from your data?
I don't personally do that, and maybe
you can start after
maybe
the
I
show.
should. Yeah, maybe I should.
It's only fair.
To be fair, they'd get so many publications, though, they probably wouldn't be able to, I don't know.
They wouldn't know what to do with it.
Exactly. Yeah.
So, and they have the sensors. They put the sensors on the satellite,
yeah.
And the sensors are what? It's visible light, you mentioned?
Yeah.
And that's just a camera, I guess, or is that more than a camera?
People in the field typically call it an imager, but it is essentially a camera. Basically, it means taking pictures, basically.
High resolution.
So that depends on the sensor. Typically, there's a trade-off. You either have higher resolution, as in spatial resolution, so you can see fine-grained detail, or you have a higher temporal resolution, so you get to see the same area more frequently. And you typically are one or the other. It's difficult to do both at the same time.
Okay, and then infrared. So it must be another kind of camera that
Right.
just takes infrared too.
Absolutely, yeah. And it's in different regions of the infrared, and some of them are better at looking at really hot things, and others at subtle, warm sort of things, and we try and use both.
And so now, I love this. So let's track the data. Okay, the data is being broadcast by the satellite and downloaded to, in this case, Google.
Right, yeah. So in my case right now, I'm using a lot of data that was originally NASA data that Google have in what they're calling the Google Earth engine.
For Google Earth, the program we all know and
Exactly,
love.
yeah.
Okay, okay.
So I guess also a team of people in Google had the idea of saying, well, why don't we make this available to other people? They have petabytes of data, so thousands of terabytes of data.
So a petabyte, it's not a pedophile, it's different from petabyte.
Different, yeah.
Now, we don't, this is a family program, okay?
Let's say
we don't
thousands
talk
of
about
terabytes.
pedophiles, talk about petabytes.
Yeah.
And that's 1,000
Terabytes.
terabytes.
Yeah.
That's bigger than a bread box.
It's a lot. It's a lot of data, and yeah, as I was mentioning before the show, just downloading data used to be a huge issue. It could literally take months to download the data you needed
don't have time
just to
for
do
that.
work, and people don't. So bandwidth is definitely the limiting issue, and Google has sort of hit on that. So what they're doing is they have all these data on their computer clusters, and they just say, have at it. We'll give you access. We'll even let you run algorithms on these data sets, and then you can just download the results. So instead of taking months to download all these images, you can just download the chart that you wanted to display on.
So, I'm really fascinated with this. So, Google is downloading. You could download yourself if you wanted. Is it still possible? But it would take months.
Yeah, exactly.
You're not shut out of downloading.
No,
you
it's
still can do it.
Still there, yeah.
And you would deal directly with NASA on that. Yeah.
Exactly, yeah.
But Google sort of puts itself in the middle, downloads for you, holds on to the data on one of its servers, and then you can query the data.
Exactly, yeah, that's exactly what happens.
It's a wonderful thing.
Oh, yeah.
So how current is the data? I guess every piece of data is going to have two elements. Aside from the data itself, it's going to say when it got that data and where it got it from GPS coordinates,
Right.
I guess.
Yes, absolutely.
So whenever you query, you know already when and where it came from, yeah?
Exactly, yeah. That's the case. I have an image that maybe we'll see later, which is actually from some activity here in Hawaii, and that was from within a month or two maximum.
That's pretty good. But let's not wait.
All
Let's
right.
go for it.
Sure, why
Carpe diem. Let's see some of those images now.
Sure.
What are we seeing?
Oh, well, this one here is of the project that I'm currently funded to do with Rob Wright at the University of Hawaii. The image on the top is a visible image of a volcanic crater lake in Vanuatu. And the one on the bottom is the same lake, but just seen in the thermal infrared. So this sort of bright green blob in the middle is showing that lake is warmer than the surroundings.
It's the same orientation? Same.
Absolutely the same, yep.
So what's really funny, because the shapes are not the same.
That is true, yeah. So that to me indicates that there's quite a bit of vapor, warm vapor coming off of the lake itself. What was surprising when I actually put this graphic together was that there's quite a strong amount of vapor coming from this sort of left blob, which I guess in the visible image looks sort of brown and has a black sort of triangle shape in it.
Yeah.
So those are the sort of new observations you can make when you're looking in different parts of the electromagnetic spectrum and not just the visible part.
Yeah, so, and the scale will be the same too. What I'm getting is that the green blob is bigger than the photograph at the top.
Yeah.
Because the heat signature is bigger when you look at it through that camera.
Exactly, yeah.
Okay.
That's exactly right.
That's pretty interesting. So what do you do with that?
Well, so what we want to do is look at how that changes through time, basically, because crater lakes are pretty unique and special. And that's because they allow us to see magmatic fluids as they come, the effect of magmatic fluids, basically, on the surface that would have otherwise have been lost, because they interact with the water in the lake, and they might change the color or the temperature or the size of the lake.
The magma you're talking about.
Right. Well, the sort of the liquids and gases coming off of the magma.
Okay.
And it's special because most volcanoes are just not monitored. There's nothing even looking at them at all, except maybe some seismic networks, but they're not dedicated.
That's so interesting. You know, we think that this is a big event,
Right.
and Hawaii News Now goes out there with a helicopter.
Yeah.
But aside from that,
Yeah.
you cannot assume that anybody's actually watching it.
Right.
Not anybody scientific anyway.
Oh yeah, for most volcanoes in the world. Obviously, Hawaii is a special case, and it's really well monitored. But most volcanoes just have nothing. And even though you could sort of change that and make that better in the future, there's nothing you can do about the past. But that's what's great about satellites, because they're up in orbit and they just keep spinning around, and they have all this data from decades ago and up until now. And so we can kind of use that to get new insights. And by looking at crater lakes, we can start to look at these fluids which tell us a lot about what's happening underneath the volcano, the sort of hidden area or volume beneath the volcano.
Yeah, yeah. So if this in Vanuatu is interesting to you, you decide you want to study it and understand what's going on now, you could go to Google and query old data.
Right.
And get 10 years of progression on this.
Exactly.
And it's a dynamic that will help you understand, yeah?
Yeah, exactly. To go back to Google Earth Engine, it really has made life a lot easier for looking at these really big data sets and coming up with new observations.
And when we come back from this break, I want to find out exactly how you make that query.
Okay.
I want to find out how you get the data down, how you study it, how you write your articles about it, you know, what it means to us, all of us. That is Samuel Murphy. He's a postdoc volcanologist at Hawaii Institute of Geophysics and Planetology in the School of Ocean Earth Sciences and Technology at UH Manoa, and he is revealing the secrets of volcanoes, eruptions, and wildfires to us here on Think Tech. We'll be right back.
Hi, I'm Ethan Allen, host of Likeable Science on Think Tech Hawaii. I hope you'll join me each Friday afternoon as we explore the amazing world of science. We bring on interesting guests, scientists from all walks of life, from all walks of science, to talk about the work they do, why they do it, and moreover, why it's interesting to you. What the science really means to your life, its impacts on you, how it's shaping the world around you, and why you should care about it. I do hope you'll join me every Friday at 2 p.m. for Likeable Science.
Aloha, I'm Kaui Lucas, host of Hawaii is My Mainland, here on Think Tech Hawaii every Friday afternoon at 3 p.m. Start your Pauhana weekend off with the show where I talk to people about issues pertinent to Hawaii. You can see my previous shows at my blog, kauilucas.com, and also on ThinkTech's.
Okay, we're back. We're live. We're here with Samuel Murphy, postdoc in volcanology at UH Manoa and the Hawaii Institute of Geophysics and Planetology. And talking about volcanoes and eruptions and wildfires. And we saw some pictures of a crater lake in Vanuatu, but you have another picture you want to show us.
Sure. Well, yeah, here is the Google Earth Engine website. So
I can get on that, right?
you can, yeah. To actually start downloading the data, though, you need to ask them. But it's pretty straightforward. I don't think it's very restrictive. As long as you have an idea and say, I'd like to use it for something, and send them your email. I think you have to have a Gmail account.
Really? That's
yeah.
all, huh? But you have a much closer relationship with Google and Google Earth than that. You're actually in some kind of grant thing with them.
Right, yeah. They awarded myself and Rob Wright, who's actually the principal investigator on this, some money to start looking at wildfires. And so that's work that's starting right now.
Oh, it's happening right now.
It's going
Oh,
to
just beginning.
begin right now.
Okay, good.
What was pretty cool
There's
is,
a news scoop, okay?
Yeah, exactly.
Scoop. Google gives Rob Wright and Samuel Murphy some money.
yeah, which is good. I should highlight that's coming from outside of Hawaii and coming in, so that's always good too.
That's why we like the university.
Yeah.
Money comes in.
Yeah, well, yeah. We like to think we are contributing positively. But what was really cool is they invited me out over there. So I got to go to Google and hang out with some Googlers.
Oh
and it
boy,
was
that
fun.
must have been an experience.
Yeah, it was
It's
really
like
good.
going to Mecca.
Yeah, exactly. Yeah. The nerds like me.
What are they like? They actually wear pants and everything?
It's kind of smart casual, I guess.
Yeah.
Nice food. They are just really nice
They
people.
bought you lunch.
Yeah, exactly. They bought me lunch, so I'm happy.
What were they like? Were they super smart?
Yeah, but not in like, you know the guy from The Princess Bride? You know that guy?
Sorry.
Oh, that's okay. But it's like, it's a nice kind of, they're nice people. They they work hard, but they're very pleasant, and you know, it's nice.
That's good. That's
Yeah.
good. So what did you learn from them when you went to visit them?
I learned all kinds of stuff. Probably the biggest one for me was how much they're kind of investing in what you'd call the cloud, I guess. So besides Google Earth Engine, they also have other products that I'll be trying to use, and I'm trying not to go into too many geeky details, but basically it could make my life a lot easier, and basically gives me access to supercomputing from my desktop or even from my laptop.
Yeah. So this is a huge boom for you. For you.
Really is.
So okay, you can download it from them, also for free, like NASA. And in fact, they give you money. And do they want anything in return?
Some good science,
Okay.
basically.
And so just on the methodology thing, so you can sit there 2 o'clock in the morning and in your pajamas
Yeah,
and
theoretically.
you can query the Google Cloud data. What's that like? You have to have a programmer's interface for
Right.
special functions and all that?
Well, there's two different ways of going about it. They have a nice website which you can interact with. That's one of the interfaces, and that's in JavaScript. And it's pretty neat because you can see the results instantly. So you can say, okay, fetch this image and display it on the Earth. So it'll put it where it's supposed to be, and you can see it and interact with it. So that's pretty neat.
Then you can download it on your own machine. You have it.
Yes, you can download it, but that's kind of contrary to what they would like you to
Oh,
do
really?
with the data.
They want you to look at it just on their server.
Yeah, basically they'd like you. You can interact with it. You can look at it on your own web browser. You can download it. It's just that's not what it's set up to do. And the reason is because if everyone's just downloading a load of data,
It'll clog the system.
yeah, and it's slow and it's inefficient, and we can still get away with doing that now, I think. But in the future, that's going to be less and less possible because data sets will just get too big compared to what our broadband can handle.
Yeah. Okay, so now you have programmer's interface. I guess you have to have some training to figure out exactly how to get this on your screen.
Yeah, well, to be clear, I hadn't ever programmed in JavaScript or Python before this project, before this year.
They show you how. Did you learn yourself?
Well, they have really good documentation, so you can just look it up and check it out. But I had been programming for a long time in a really esoteric language.
Which was?
The IDL. But no one uses, it's very specialized. So all astronomers
Scientific
and
language.
remote sensing people might use it, but it's nowhere near as big as something like Python or JavaScript.
Yeah, so this suggests, does it not, that you can have these specialized IDL type languages, but what's really happening, what's moving, science is moving to the more common languages that are used
Right.
on the web, open source
Exactly.
languages on
Yeah.
the web.
Exactly.
It's very interesting progression.
Yeah, it is, and it just makes life a lot easier.
Yeah.
Basically.
Okay, so you download's the wrong word, but you get the data, the graphics, whatever it is. What do you do with that in order to make your scientific discoveries, conclusions?
That's a good question. I guess it kind of depends on the project, but for me, I'll be trying to look at how the different metrics that I'll be looking at, so the color, the temperature, and the size, change through time, at least for this Crater Lakes project. For the wildfire project that's just starting, what we're going to try and do is detect the wildfires and then take in a whole bunch of other data and predict which direction they're going to propagate and how quickly. And so what we can do, what's neat about having the whole image stack throughout time, is that then we can look at a later image and see if where we said it was going to go is now burned.
You can see if your prediction or
Yeah,
predictability
exactly.
is right.
Exactly. Yeah.
That's great. So you can test on your own theories that way.
Yeah.
Yeah. So, okay, but you mentioned you want to be able to predict how the wildfire is going, but can you predict that there will be a wildfire based on what you find in the eruption and the lava flow itself?
Oh, so just to be clear, these are separate issues in that although yes, volcanic eruptions can cause wildfires, and that's a significant issue here in Hawaii, we'll be sort of separating those two in that we'll be looking at volcanic crater lakes, which is just the aqueous sort of lakes, and wildfires as a separate issue. But to answer
So
your
you
question,
don't really care about the causation?
Oh,
It'd be a wildfire from any cause at all, right?
well, maybe I'm dancing around the question a little bit just because it's difficult to predict exactly where a wildfire will occur before it has occurred. A lot of people have developed hazard risk maps, and they exist, so you can see where it's more likely to happen. But because most wildfires are caused by people, you don't
It's unpredictable.
really
People
know.
are
Yeah,
unpredictable.
Yeah, exactly.
Yeah.
But
So,
what
and a
sorry.
wildfire is like a forest fire. Yeah.
Yeah, exactly. That's what it is.
Mm-hmm.
But it can be in grass, it can be in shrubs, it can be just anywhere basically out of an urban area, I'd say.
Yeah, let's look at the hotspot photo and see what we can learn from that. Okay.
Oh, right. So this is a website that's hosted by HIGP, and you can go there to look at hotspots. This website's been running for decades, and basically I hope to contribute to it. So you have these different categories of data. There's GOES, MODIS, and there's the vent monitoring at Pu'u'o'o. And you can go in there, explore, grab the data, and what you see is, what's available is a collection of detections of hot targets. So volcanoes, some fires too.
Now.
Yeah,
Now hot
from now
targets.
until way back in the past.
Oh, okay.
And-
What they look like.
Well, actually, I have an image to show, which might help.
Let's see what it looks like. Yeah.
Yeah, that might help to
Yeah.
describe that. So,
Okay, what is this?
that's actually really helpful. So, in the top left is a geostationary satellite image of the Big Island, and you might have to look in really carefully and actually already know where Halemaumau and Pu'u'o'o are, but there are some pinkish orangish pixels there. So it's quite a low spatial
This is the
resolution.
top left. Yeah.
Top left. And, but the temporal frequency or resolution is great. It's every 15 to 30 minutes, so you can look at dynamic and ephemeral events, as long as you can detect them with such big pixels. On the top right is another low spatial resolution product that was developed at the University of Hawaii, and there you can see hot targets also detected and highlighted in orange and with a green outline. So on the bottom screen, though, that's a higher resolution, spatial resolution image. And you can actually make out the craters, the lava flows. The blue region to the top is healthy vegetation, and the black region to the bottom is the ocean. And you can even see individual clouds and everything, and all these different components of the image. So that makes it much easier to determine what you're looking at, what's the size, what's the real energy coming from there, and those kinds of details, I guess. But we've never really developed a global monitoring system using this kind of data. And this kind of data has been available for decades. The reason that we haven't done it yet is because traditionally, like I said before, you have that trade-off. Either it's a high spatial resolution but infrequent image, or it's a low spatial resolution, but it's an image you can get frequently. So what's changed? Why are we starting to look into this now? The reason that we're looking into this now is because there are other players in the game. Previously, NASA was basically holding a flag by itself and doing a whole bunch of missions, including this Landsat mission. Now, people like the European Space Agency, they're also developing Landsat class sensors, and they've collaborated together to make them play nicely, basically. And so once we have lots of these kinds of satellites in space, then we can have the best of both worlds. We can have this high spatial resolution, but we can also get imagery of the same place more frequently.
From different points of view, different satellites.
Exactly.
I hope they're all as generous with you as NASA and Google is.
Well, ESA has committed to following suit, at least for what they call the Copernicus program, which is this very large Earth observation program, which includes a Landsat class sensor and another bunch of sensors.
Okay, so just one more thing is that so with this data and this kind of photography, if that's the right word, you can do dynamic measurement of hotspots that are either volcanic hotspots or, for that matter, wildfire hotspots, and you can from a past, present, future kind of point of view, you can predict what's going to happen. So, is it that from the hotspot you can tell when there's going to be an eruption of a volcano?
Some people would argue that that's the case. Predicting when a volcano will erupt is difficult. You need to take lots of different measurements. The analogy that I heard that I quite like is it's like a doctor, like a medical doctor. When he goes to give you a diagnosis, he won't just take your temperature. He'll take your temperature and he'll take maybe your blood sugar levels or your pressure or see if you can walk in a straight line or read a chart or something. I don't know, but a whole bunch of tests. And with these whole bunch of tests, he can give a much better diagnoses, or maybe some x-rays, or what, it doesn't matter, of what's really happening. So when it comes to volcanoes, I think, although our work is very valid because we're developing techniques to really quantify what's going on, but to truly understand what's happening with these really complex and large physical systems, you need a whole load of perspectives, like you're saying, so that you need to look at the hot
So
things.
with this global system, you're going to get more data.
Yeah, absolutely.
And you're getting more sophisticated at analyzing it too. Yeah.
We like to think so.
Yeah. And the same thing with the wildfires. With enough data from different places, I guess the same sensors that you're talking about, this international effort, will allow you to make a better guess on the wildfires, to distinguish them as wildfires, but also to get a beat on where they're going, how long they're going to last, cranking in weather information,
Right.
Cranking in vegetation information, who knows what.
That's right, yeah,
Yeah.
absolutely.
So what's the future of your science?
That's a good question. One of the things that I'd really like to do is contribute. So with this Google Earth Engine capability to look at this enormous data set, we can actually start to quantify the fires in the past. One of the neat things about that is that we're almost guaranteed to have missed a lot of fires with the current monitoring systems because of the low spatial resolution. So we're talking pixels that might be 1 kilometer by 1 kilometer. They're really big. So unless the fire is also really big, you might miss it.
Mm-hmm.
So we're going to try and reanalyze what happened and use these high spatial resolution images to see if we can find some of those missing fires.
Mm-hmm.
Yeah, so that's the near future, I'd say. Longer down the road, I'll have to see, what comes up.
You're still young. You'll find something to do with this. Where will I see your work? Where can I see it?
So in international publications, typically, so things like remote sensing of environment and the Journal of Volcanology and Geothermal Research. Or you can just look it up on Google, I suppose. It's probably easier. That's what we do.
Google has everything.
Exactly.
And you can look up Samuel Murphy, postdoc, a volcanologist at HIGP in SOWEST. And you can find out what he's doing in volcanoes and eruptions and wildfires, not necessarily cause and effect. How interesting. here on Research in Manoa. Thank you much, Samuel.
Thank you. It's been a pleasure.